Welcome to Easy Mathematics and a new video. It's Christmas time and I thought about a beautiful topic for a Christmas lesson, and the topic is, as you can read, 3D complex numbers, or also known as tricomplex numbers. So before we start and go into some details, first I want to explain what we want to do exactly. Then we make a small introduction, some recalls, and then point 3 is the main part, the 3 complex numbers. Of course, first we define them, and then we take a look at basic operations. Then we talk about inverse elements and the modulus. Then we talk about a little bit of matrix representation for the multiplication. Then we take care of the square root of a 3 complex number. Then we define the so-called polar cos exponential functions, and we will see why the name is meaningful. And yeah, of course, we try to find some analog formulas for the 3 complex numbers, for example the Moivre formula, or also for the cos exponential functions we want to find addition formulas. And then we see that we can write these polar cos exponential functions in an elementary way. And then the last point is the derivative of those functions. This will be the first part of this video, and maybe there is a second part, and the second part is about geometric interpretation and exponential form. And then we make some calculus, talk about 3 complex sequences, definition, convergency, and criteria. Then we could talk about 3 complex functions, definition, examples, continuity, differentiability, and Riemann equations, and power series. And then we could also talk about integrals. For the second part, I do not know if I can prepare a second part. We will see. But the first part is enough to give a motivation to try to define this stuff by yourself, I guess. A really nice topic. And as you know, there will be also small tasks in the video. And yeah, the most stuff we will prove. It's very easy if you have some basic knowledge. And yeah, we start. First, I assume that for this video that you know the basic of complex numbers. We will recall them in the video also, but not in detail. And also you have heard about the quaternions. Then I assume you know about basic properties of trigonometric functions, especially the analytic definition and relations between them. Then basics of calculus, so I will not explain in detail what is a derivative. And basics of linear algebra, so we will need a definition of the matrix, then the definition of multiplication, the determinant, and diagonalization. And I will not explain this in detail, so please make sure you have enough knowledge. But I guess it's also interesting even if you have not known about diagonalization or stuff like that. And our goal is we want complex numbers t of the form a plus ib plus jc, where a, b, c are real and I and j are hypercomplex units. This is our goal. In other words, we want something between the 2D complex and 4D complex numbers, so 3D complex numbers. Okay, this is our goal. And now, like I said, we make a small recall about complex numbers. Yeah, what is a complex number? A complex number z is of the form x plus iy, where x and I are real, and I has the property that I squared is -1. Okay, and then Yeah, addition is defined via addition of components, and the multiplication, if you multiply two complex numbers, if you distribute them naively and use I squared minus 1, we get this expression, and then we can use it as a definition, okay? And then we can define complex conjugates and real part and imaginary part, and for a complex number, the complex conjugate is the change of the sign in the imaginary part. And what is the imaginary part? The imaginary part is the number connected to this imaginary unit I, and the real part, yeah, the number connected to the unit 1, if you like. Okay, and then yeah, we have some nice properties like addition is commutative and associative, multiplication is commutative and associative, sums and products of complex conjugates are the complex conjugates of the sums and products, and some more. Yeah, like I said, I assume some stuff that you know about complex numbers, so you know that there's a trigonometric and exponential form of a complex number. So the exponent of I times y for a real number I is cosine y plus I sine y. And if you haven't heard about that, we prove this in a sketchy way. Yeah, so if you take the series definition of the exponential and plug in I times y, then we can separate this sum in the real part, so all even indices, they make the real part. All the odd indices make the imaginary part with alternating signs. You can think about that. I squared is -1, so I cubed is -I fourth is +1, and so on. And if you take a look at these series, this is exactly the analytic definition of cosine and sine. And a complex number z, we can write also the modulus of z times cosine phi plus I sine phi, where the modulus we get by the Pythagorean theorem, so real part squared plus imaginary part squared, and then the square root out of this, and the angle phi or phi we get via imaginary part over real part. And then we have to take care in which quadrant we are, and so on, okay? But this is just for a small recall. And for the quaternions, these are four-dimensional complex numbers set of the form a plus I, b plus j, c plus kd, where a, b, c, and d are real numbers. And these imaginary hypercomplex units I, j, and k, they satisfy the rule I squared equals j squared equals k squared equals I times j times k equals -1. These are the so-called Hamilton rules, and these four conditions here, they lead to the multiplication rule between the hypercomplex units. So I times j is k, j times k is I, and so on. And notice that these multiplication rules, they are not commutative. Yeah, so I times j is k, but j times I is -k. And yeah, and also here we can define a real part and imaginary part, and here the imaginary part would be a vector with 3 components. We can define complex conjugate and stuff like that. And we have like following properties: that the sums are commutative and associative. This is quite obvious, but the products are not commutative, and we can see this of course by the multiplication rules here, okay? And Hamilton had a dream. He thought about, what about three-dimensional complex numbers, trienions or tricomplex numbers? And the question for him was, which multiplication rules do I need to have some nice structure? And we could think about a tricomplex number set of the form a plus ib plus jc, where a, b, c are real, and I squared equals j squared equals I times j equals -1. But if you play around with these multiplication rules, we will see that this will lead to a contradiction, and I leave the details for you. And then is of course the question, what can we do to make Hamilton's dream become true? And these are the tricomplex numbers. Yeah, and we define them first, okay? So tricomplex number, we call a number t of the form a plus ib plus jc, where a, b, c are real numbers, a tricomplex number with Hamilton rules. I squared equals j, j squared equals I, 1 times I is I times 1 is I times j is j times 1 is j, and I times j equals j times I and equals 1. And for the set of all tricomplex numbers, we write capital T. Yeah, this is the set of all tricomplex numbers where the components are real numbers. Okay, yeah. And these Hamilton rules, I prepared a multiplication table, yeah, to see what's going on in a table form. Yeah, so these rules here are summarized in this multiplication table. Okay. Then of course we need a definition for equality and neutral elements, and we say two tricomplex numbers t1 and t2, they are equal if and only if they are equal in each component. This makes sense, and we can define the neutral element of multiplication, so the 1 of three complex numbers is 1 plus I times 0 plus j times 0, and the neutral element of addition, the 0 three complex, is 0 plus I times 0 plus j times 0. Alright? And now we define addition and multiplication also very naively, so for the multiplication, if we have two tricomplex numbers t1 and t2, then of course addition is defined via the addition of each component. Yeah, so the two parts with the unit 1 we sum up, then the two parts with the unit I we sum up, and so on. And we see that the sum of two tricomplex numbers is of the form of a tricomplex number. This is very nice. And for the multiplication, if we distribute it naively and use our multiplication rules, yeah, so for example, y is here b1 and c2. Why that? Because I times b1 times j times c2 is b1 c2 times I times j, and I times j is by definition 1, so it belongs to the component of the unit 1, and so on. Okay, so pause the video and check it for a short moment that this is correct. And here also we see that this is a tricomplex number again, and this is what we want. Yeah, so we have addition and multiplication. And now we come to the first theorem, and this is following: addition and multiplication are commutative and associative. So in other words, for t1 and t2 element of the three complex numbers, we have t1 plus t2 equals t2 plus t1, then the associative law, and for the multiplication the same. Yeah, and we prove them, of course, and I guess that you agree with me that 1 and 2 are very obvious. 3 is obvious by the multiplication table. 4 is maybe more interesting, and we discuss 4 in a detailed way. So, okay, one moment. Okay, here we are. So we start with t1 times t2, quantity times T3. We use the definition of T1, T2 and T3, so they are from the form AI plus IB, so AK plus IBK plus JCK. Okay. Then we multiply T1 and T2 with the multiplication rules we've seen before. This becomes the second line. Then we multiply again, so we distribute again with the multiplication rules, and this becomes the third line. So here is the component belonging to the unit 1, here is the component to the unit I, and here is the component to the unit J. And now, if we take a close look, we can rearrange each component in this following way. And then if you take a close look, we go backwards, so we can factor out A1 plus IB1 plus JC1, and we are left with this square brackets, and the square brackets, they factored as 2 times T2 times T3. Okay, so it's not so difficult. Yeah, you have to take a pen and paper and make sure that this works. This is a very nice property, so multiplication is associative, very nice. Yeah, and task 1 is prove property 3. Maybe it's not so long, but it's a nice way to get a feeling for these numbers. So property 3 was T1 times T2 is T2 times T1. Yeah, so prove it with pen and paper. I know that for the multiplication table it's more or less obvious, but it's a nice exercise to get the feeling for this number, so I extremely recommend to do this. Alright, task 1 is done. Next, we want to talk about inverse elements, and yeah, the definition is, or the definition of an inverse element is if we can find a second number which sums up to 0. Okay, and then we make a theorem out of this. For all tricomplex numbers, there is a unique tricomplex number u such that t plus u equals u plus t equals the 0 element of the tricomplex numbers. And then we say u is negative t, and we call it the additive inverse of t. Okay, and yeah, such kind of theorems where it's said to be there is a unique element which satisfies some properties, we have to show two things in the proof, and the first thing is the existence, and in this case the existence we make it constructive, and yeah, we let t be a tricomplex number of the form a plus I b plus c with a, b, c real numbers, and then we choose u minus a plus I times minus b plus j times minus c, and then we see if we calculate t plus u, so a plus ib plus jc plus minus a plus I times minus b plus j times minus c. So all the numbers are real numbers of the components, and here we have the addition, and we know how to add. We can add each component, so we have a plus minus a and b plus minus b and so on. And in the components there are the laws of the real numbers, so a plus minus a is 0 and so on and so forth, and the tricomplex number u plus I times 0 plus j times 0 we have called the 0 element, and therefore because plus is also commutative, we have u plus t is t plus u is 0t, so we know that inverse exists, and now we have to show that this inverse is unique. And very typical for uniqueness proofs is we assume there are two inverses of the tricomplex number t, we call it u1 and u2, and we want to show that if there are two inverses, then they must be equal. Okay, and how can we do this? Yeah, because u1 and u2 are inverses of t, we know that u1 plus t and u2 plus t is the zero of the three complex numbers. And therefore, we can set them equal. u1 plus t is u2 plus t. And by definition of equality, we know that three complex numbers are equal if each components are equal. So we have the three equations: a1 plus a is a2 plus a, b1 plus b is b2 plus b, and c1 plus c is c2 plus c. And now we can solve linear equations in the real numbers, and we know how to do this. So we subtract from the first equation a, from the second b, from the third c, and we are left with the equality of the components of u1 and u2. And by definition of equality of three complex numbers, we can see that u1 is u2, and therefore every three complex number has exactly one additive inverse. Very beautiful, huh? Alright, additive inverse. What about multiplicative inverses? Yeah, for a three complex number t of the form a plus ib plus jc, where abc is not zero, or this crazy expression a squared plus b squared plus c squared minus ab minus ac minus bc is not zero, then we have a unique u such that t times u equals u times t equals the one element of three complex numbers, and then we say u is the multiplicative inverse of t, and we denote it as t to the negative 1. Yeah, there are some restrictions. Yeah, as long as these two conditions here, then we have a multiplicative inverse. And yeah, before we prove this in a sketchy way, there is a task 2, and yeah, which of these sets are closed under multiplication? So being closed under multiplication means if we take two numbers of a set and multiply them, then the result belongs to the set. If this is satisfied, then we say a set is closed under multiplication. And yeah, we have three sets: S1, S2, S3. S1 is the set of three complex numbers with the condition a plus b plus c is 0. S2, similar, the sum is 1. And S3 is this crazy expression from above, but not equals 0, it's equals 1. Yeah, you can play around with that, with which sets are closed under multiplication. And task B is also very nice. We define the quantity magnitude q of t for a three complex number t of the form a plus ib plus jc, as q of t is defined via the cube root of a cubed plus b cubed plus c cubed minus 3abc. And with this definition, prove that qt is multiplicative. So in other words, q of t1 times t2 for two three complex numbers is the product of q of t1 and q of t2. Alright? Yeah, and how to prove this multiplicative inverse? Yeah, so you can set up a system of linear equations and then try to solve this, and then we will see that in the denominator we have some expressions where these two are part of. Yeah, I leave that as an exercise for you. Yeah, it's a linear equation. I will not want to discuss this in detail. I leave this to you. Yeah, and the next point of our journey of three complex numbers is the modulus. Yeah, and we define the modulus of three complex number via the Pythagorean theorem. So the modulus of x plus iy plus jz with index t for modulus in the three complex world is defined via the square root of x squared plus y squared plus z squared. Okay. And there is also a small task. First, show that the modulus of t1 times t2 is bounded by cube root or by root 3 times modulus t1 times modulus t2, and the modulus of the reciprocal of a tricomplex number is bounded by below of the reciprocal of the modulus. So yeah, this is maybe also a nice property, some bounding properties. Yeah, have fun with this task number 3. And like I said, I just want to give an overview about important definitions, so we will not go in too much detail. 3.4 Matrix representation for multiplication. Yeah, so let T be a tricomplex number, and we define the matrix M of T. Yeah, and the first row is ABC, the second row is CAB, and the third row is BCA, where ABC are the components in the tricomplex number. And now let T1 and T2 be two tricomplex numbers. I don't get this away. Yeah, show that MT is multiplicative. So in other words, M of T1 times T2 equals M of T1 times M of T2, and find also the determinant. And yeah, it's not so difficult, but it's a nice result, especially the determinant. Yeah, so this will remind you of something what we have done previously. Okay. Yeah, this was the modulus, and now we could think about square root of a tricomplex number, and we define the square root. So if for a tricomplex number t, a tricomplex number u exists such that u squared is t, we say u is a square root of t, and we denote this as u is square root of t. Okay, and yeah, the question is, when do we have square roots, and are there conditions? And here's a theorem 4. A tricomplex number has a tricomplex square root for following cases. If t is of the form a times 1t for real a, so in other words, t itself is a non-negative real number, or t is of the form a plus ib plus jb, where a is greater than 0 and b is bounded by negative a over 2 and a. Then we have a square root. Task 5. Let Tc be the set of all tricomplex numbers with complex components. Then it's quite obvious that every tricomplex number with complex components has a square root, and show this constructively. And pardon, this should be j, of course. Okay, so show constructively that every tricomplex number with complex components has a tricomplex root with complex components constructively. All right. Yeah, and now we take care about the theorem 4. We prove this. And we make this in a sketchy way. Like I said, I assume that you know about a little bit about linear algebra. Yeah, so for a tricomplex number, we use the matrix representation MT, and over C, MT is of course diagonalizable. So we can find the diagonal matrix D and transformation matrices J and its inverse. Yeah, you know that on the diagonal there are the eigenvalues and the columns of J are the eigenvectors. And then we can apply a function to a matrix, and if we diagonalize it, then the function only affects the diagonal matrix and not the transformation matrices, and this is a very nice property, and we will use this here. We will not prove this in detail. Yeah, and if you diagonalize this matrix MT, you get on the diagonal the elements a plus b plus c and a plus 1/2 times with some transformation matrix J, which is here not important. And then on each diagonal element we take the square root, and now we see that what can we see? We see that in the second and third diagonal element there is a minus quantity squared. So this is non-positive, okay? So it's equal or less than 0. But what we actually want is that this radicand is greater or equal to 0, and the only case what we can reach is that b equals c. So in other words, this leads to a is bigger than b. Yeah, so what we want here is we want non-negative radicands under this inner root to avoid the complex numbers. And if b equals c, then this becomes 0. And then if b equals c, we have here minus 2b. So we have a minus b. And then the square root, so a must be greater or equal to b. And with the first entry, we see that a is greater than 0 and b is bounded by negative a over 2 and a. Alright, so this is the condition to avoid the complex numbers. If this condition is not satisfied, then we see we need the complex numbers. Okay. Yeah, here it's a nice exercise to determine the eigenvalues of these matrices. Yeah, have fun with this. This proves our theorem. So the next point on our journey are the polar cos exponential functions. And yeah, it is natural to define the exponential of a tricomplex number via its series expansion. So if we take the series expansion for the exponential, so the infinite sum with index k over t to the power k over k factorial, and we plug in tricomplex numbers, it can be shown, it's not so difficult, that we have the basic exponential rules. Yeah, so the exponential of a sum is the product of the exponentials. This is also valid for tricomplex numbers, and motivated by the Hamilton rules, and I'll let you to think about that, we define the polar cos exponential functions. The name I explain later why we choose this name, but what we define are three functions: cx, mx and px of y. Also infinite series with 3k, 3k plus 1 and 3k plus 2. Like I said, this is motivated by the Hamilton rules, and I let you to think about that. And like I said, we see later why these names cx, mx and px are meaningful. Just a moment. Theorem 5. For real y and the Hamilton rules, we have exponent of I times y, where I is from the three complex numbers, okay, not from the complex numbers, it's from the three complex numbers. So exponent of I y is cxy plus I mxy plus j px of y, and exponent of jy, where j is the second imaginary unit of the three complex world, is cx of y plus I px of y plus j times mx of y. And in the classical complex numbers, we have exponential of I times y is cosine y plus I times sine y. So this is an analog. So the cx, mx and px, they play the role of the trigonometric functions, but they are not classical trigonometric, and so we call them polar functions. And there is this cos exponential, and we will see later. So the name polar is okay so far. And yeah, we prove the first identity. And yeah, what we do, we plug in I times y in the series definition of the exponential. Then because multiplication in the three complex world is commutative and associative, we can distribute the power, so the exponent we can distribute. And then we write these sums. So we split up the index k in 3k, 3k plus 1 and 3k plus 2. Alright. And why we do this? Now by the Hamilton rules, we see that all indices which are divisible by 3, they become the unit 1. All indices which leave a remainder of 1 after division by 3, they belong to I, and remainder 2, they belong to j. Okay, so like I said, this is easy to see with the Hamilton rules. And now we take a look at these three sums, and this is exactly the definition we have seen before. These are these three cos exponential functions, and for exponential of j times y, we get the similar result. I show it again. Yeah, so mx and px, they change the role. You know the addition formulas for sine and cosine. I printed it here again. And yeah, we can think about addition formulas for the polar cos exponential functions. Yeah, why not? They play the role of the trigonometric functions, and maybe they are some nice addition formulas, and here they are. So I will not read them in detail. You can pause the video and read them by yourself, okay? But you see that there is some kind of similarity, yeah. And we will prove not detailed. I leave the details for you, and we prove all three of them, but like I said, not detailed. I make a sketch, and I recommend to take pen and paper and prove them with the help of the sketch by yourself. We consider the exponential of I times y plus z. where y and z are reals and I is the imaginary unit from the tricomplex number, not from the complex number. Yeah. And yeah, we have seen before that exponential is if we have a sum in the exponent, yeah, and it becomes a product. And the left-hand side can be expressed using the previous lemma. And there's a link in the download description. There is a download link in the video description. So we have seen an expression from the left-hand side a couple of minutes ago, and the right-hand side can be expressed using also previous lemma. And then if you distribute everything and use the Hamilton rules, we can compare the components and we get the result. Alright? Yeah, and there is an obvious question. Is there a Pythagorean theorem for three complex numbers? Yeah, I have printed 4 identities. You can decide for yourself which you will see as a Pythagorean theorem. So for example, the first one, the squares of the sum of the squares of the 3 polar cos exponential functions. It's a sum of 2 exponentials. So this is not constant. But if we take the cubes and sum them up and subtract 3 times the product of these 3 functions, we get 1. So maybe if you like, this is our Pythagorean theorem, but I leave it to you what you will see as a Pythagorean theorem or not. Then if we have like mixed products and then we sum them up, we get also a similar sum of exponentials. And the last identity is exponential of I minus j quantity times y. We can write this in following form. So the analog of the Morpheus formula. What was the Morpheus formula? In the classical complex numbers, there is the nice property that multiplication is addition of the angles. Okay, so this is why this is so beautiful. It seems like we can distribute these n into the trigonometric functions, and this is a very nice property. So cosine y plus I times sine y to the power n is cosine n times y plus I times sine of ny. And yeah, we want something similar, and here it is. Let n be a positive integer. We have 2 De Morpheus analogs. So the first one is cx plus imx plus jpx to the power n is cx ny plus imx ny plus jpx of ny. And then a similar identity changing the role of mx and px. Okay. And yeah, we prove this not detailed. It's very messy, and I will show the results in a couple of seconds. But if you prove this with pen and paper, it becomes really messy. I will not prove it in detail. What you basically use is, because the exponential, so the power of an exponential is, yeah, you can distribute the exponent into the exponential. This is like the classical rule for exponentials. This is also valid for 3 complex numbers. Yeah, and then with previous results, we get these 2 De Morpheus analogs. Alright, I leave the details for you. I will not write all the stuff here because it's very messy. But We have another nice theorem we will take care of, and yeah, we have seen the addition formulas with two summands, and then we can get the special case if the two summands are equals, or like the double angle formulas. And yeah, it's always funny for mathematicians to generalize stuff. So what if we plug in multiple arguments in the tricomplex polar cos exponential functions? And I have to say that what we can expect, like in the trigonometric case, there is some binomial theorem going on. So we have binomial coefficients and mixed terms with sine and cosine and some exponents. And here, because we have three parts, yeah, maybe you guessed it, we have trinomial coefficients, but in a not so nice way. And please read carefully what is going on here. So this is the first multiple argument formula. Then for mx it becomes more worse. So see that here we sum over all partitions of natural numbers, t1 plus 3, t2 plus 3, t3 plus 2k. Here it's k plus 1, and also in the third case it's k plus 1. And then in the trinomial coefficients we have here a k and here a k, and these elements of the trinomial coefficients, they correspond also to the exponents, okay? And here we have 3t2 plus f of k and 3t3 plus g of k, also that corresponds to the exponents here. And here f and g, they change the role. And what is f and g? Yeah, f and g is following expression. Like I said, if you play this game with pen and paper and make it carefully, it's really messy, and then there is some structure which you can analyze, and this is what I came up with. I'm pretty sure that fk and gk can be also chosen by certain sequences. The first three elements are enough, but yeah, I decided to make it in a parabolic way. Yeah, it's not the nicest expression, but it's an expression. Yeah, and yeah, we proved this. Yeah, we proved this. The first step is we have a trinomial here, and we raise it to the power n. So here are the trinomial coefficients, and then we have cx to the power t1, I mx to the power t2, and j px to the power t3. Now we can distribute the exponents into the product, okay? And now what we have to think of is which of these exponents and products of I and j how do they contribute to the units. So if we take the unit 1, we get the unit 1 if I and j are multiples of 3. Alright, this is our first. We get 1 if I is I and j stays j, because I times j is 1. So this means if both exponents leave remainder of 1 by division of 3. and we contribute to 1 if I becomes j and j becomes 1. So in other words, if these two exponents have remainder 2 after division by 3. Alright? And now we see that these three sums, we can write these three sums by adding a plus 2k here. So in here 0, 1 and 2, and here 0, 2 and 4. This is our first expression here, okay? And what contributes to I? To I, we have, for I we have if, here is it, for I we have if I stays I, so in other words remainder 1 after division by 3, and j becomes 1, so the exponent is a multiple of 3. We get I also by j squared, so in other words, if I is a multiple of, the power of I is a multiple of 3 to become 1, and j, the exponent of j leaves remainder of 2 after division by 3, so we have 3 j squared, j to the 5th, and so on. This contributes also to 1, to I. And the last contribution to I is if, yeah, if the exponent of I leaves a remainder of 2 after division by 3, and j leaves a remainder of 1 after by division to 3. Yeah. And now we see here we have the form of k plus 1, so 0 plus 1, 1 plus 1, and 2 plus 1. And here is a mystery structure going on, and if you write it down carefully, you can see that this can be expressed with the parabolic equations we have seen. And yeah, for j, we played the same role also for j. If we take a look what contributes to j, and also what contributes to j contributes if I becomes 1 and j stays j. To j contributes if I becomes j and j becomes 1, and to j we contribute to j if I stays I and j becomes 1. And then we see that this is with the exponent rules x plus I and x plus j px, and then we compare the components by definition of equality. Okay, so like I said, there is a link in the video description, so download it, study it carefully, take pen and paper. It's nice to play around with stuff like that. And yeah, the second generalization addition formulas for find expressions of the form a plus ib plus jc for following terms. Not the multiple argument formula, so if the arguments of cx, mx, and px itself are sums, so we have seen the special cases if all jk are 1, and yeah, your task is to find expressions in terms of cx, mx, and px. Have fun. Yeah, we come more or less to the end. And like I said, polar cos-exponential functions and their elementary representations. Now we see why these names are meaningful. And first of all, if you play around with this series, you can do this in different ways. You see that you can write these three functions in following form. And now we see why they are called cos-exponential, because we have exponential and a cosine here. This reminds of the c, so cos-exponential. Then the m, because here the cosine is the same but with a minus shift, this is the minus cos exponential, and here similar with a plus, this is the plus cos exponential. And this is why these names are meaningful. Yeah, so we have cleared this also, and yeah, I give a proof of this also in a sketchy way. So we have seen exponent of I times y is cx plus imx plus jpx. So yeah, if we plug in 2y, we get cx 2y plus imx 2y plus jpx 2y, and we can rewrite the exponent of I times 2y in following form. We can write I times 2y via I plus j times y plus I minus j times y, and then separate with the exponent rules I plus jy times exponent of I minus j times y. And by task number 6, we have seen that the exponent of I minus j times y is this crazy expression. And similar we can find for I plus j times y, and then we can compare the real and hypercomplex parts, and this results in expressions for 2y, and the last step is replace 2y to y and we get the result. Okay, this is a sketchy way. I leave details for you if you want to play around with this. And before we end, we have a last theorem. For real y, we have the following relations. So the derivative of the cos exponential is the plus cos exponential. The derivative of the minus exponential is the cosine exponential, and the derivative of the plus exponential is the minus exponential. And of course, these three functions cx, mx, and px, they solve the linear differential equation y3 prime equals y. And yeah, this can be seen with the series expansion immediately. Yeah, this is not hard to check, but I want to prove it not with the series, because yeah, we have to talk about convergency of the series and differentiability of series and stuff like that. But if we use the elementary representation, we know the rules, and yeah, I show it as an example for the cx. So if we differentiate after y, 1/3 exponential y stays 1/3 exponential y. Here the 2/3, it comes in front. Then we have the product rule, so cosine becomes minus sine, and then with the chain rule, q put 3/2 comes to the front. And also, if we differentiate the second factor, e to the minus y/2 stays e to the minus y/2, and there's a factor minus 1/2. Okay, and the first factor stays the same. Then we take a close look that we can write minus root 3/2 as minus sine 2 pi over 3, and minus 1/2 is plus cosine 2 pi over 3. Okay. Now we can use the addition theorem for the cosine and get here the plus 2 pi over 3. Finally, we see the derivative of cx is the plus cosine exponential. And this is the first part of this video. Hope you enjoyed it. See you next time, and bye bye.